Hello, students. We are now getting into the main focus of this course. That first little bit on the algebraic thinking is kind of a wrap over. This is just no way to fit it in one semester. So we include the algebraic thinking with the rest of geometry. This is the first chapter in geometry. We do 11, 12, 13, and 14. So 4 total chapters related to geometry. All of them have kind of a different focus. Many of them include the same concepts. So you're going to see a lot of connections of ideas. We'll start off with 11.1, which is basic notions. Then we'll talk about curves, polygons, which is a big part of this. Poly for many, many-sided. The gon is the side, so polygon just means many sides. Later, we'll get to 3 dimensions in geometry, and we'll see things called polyhedron. And a hedron is like a head, so like a face. So it's many faces. And those are just 3 dimensional shapes, like a cube. If you think about it, that has many faces on it. Whereas in a polygons, they're going to be 2 dimensional and they're going to be flat. So squares, rectangles, triangles, a rhombus, things like that. Okay. The question down here is a pretty good one. I love this kind of question. So the person's trying to make a bunch of triangles, and you could actually solve this problem. You don't need too much to do. Treat this as a vertex. So it says the 4 corners are also vertexes, but they're going to cut this into triangles. And it looks like you're like, wow, that's going to be tough. But remember, a triangle is 3 angles, and if it has 3 angles, it has to have 3 sides. So what you can do is when you notice a particular connection, like this dot right here is pretty close to the 2 orange ones, you could connect them and say, okay, there's a cut. So that would be one triangle, right? Now take a look at this dot and the corner dot and say what dot is next to it closest. And you say, okay, this one, perfect. Guess what? Boom, boom. There's triangle number 2. Okay. Now you can come over here and say, okay, well, where else could I go? Well, this dot does not connect to the corner, so I couldn't use it there, but I could use it here. There's 3. See what I'm saying? Like it doesn't take a lot. And all of a sudden you get this beautiful shape with all these triangles cut into it. And this is actually some of what they do. Not exactly this way, but similar to what they do if they're making stained glass. They'll have these leaded pieces, and then they'll take the chunks of glass to kind of fill in the shape that they want. So pretty interesting there. Okay, so again, find something close. Again, when you look at it, if you look and you say, oh, I want to go all the way over to here, well, you've trapped one inside then, right? And so you got to be really careful when you're trapping one inside. So if you did do that, notice you've got a point in the middle that doesn't have triangles. Okay. So then what you can do is we'll just break that one. Bing, 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 right? There you go. Now I made 3 triangles out of that, and I can continue on with my next cuts. So be in charge. A little fun with that one. I enjoyed that problem. All right, let's move on forward to basic notions. Right. Big thing for this section. If I were you, and I'm just encouraging you to do this, this is not a you have to. There's going to be a lot of terms. And I'm not even kidding. There's a lot of terms. And that's because when we deal with geometry, if we say one word that means a concept, it saves us from describing it with sentences. So we try to use very specific terms so that we don't have to have long descriptive sentences. But realize Common Core wise, we've got grade, it starts in kindergarten. Geometry starts in kindergarten, and it is now woven throughout. You may or may not have had this experience. Some students have had a bit of this, but maybe not as much as the Common Core does now. Others may not have had much of this at all until maybe high school when you took a geometry class. So we're going to kind of integrate that here. So again, this is all the information from kindergarten, grades 1 through 3, grade 4, and grade 5. So again, definitely these pieces are well within what you should see at the elementary school level. Okay. Now here comes the fun of geometry. Whenever we start describing things, we get down to what we call the base level. That means we can't go and describe it any lower than that. And because of this, we can't really have a true definition for it because it's like this is just the concept and it is kind of what it is. For example, a point you kind of know what a point is by saying this is a point. But how would we define that point? So some people have tried, they'll say, okay, it's like a line that has 0 length. And you're like, what? But in order to define point, I needed the word line. And usually the word line is an infinite collection of points distinguished between two. And you're like, well, wait, I just used point to define line and line to define point. And we get this kind of circular definition. Mathematicians avoid circular definitions. And that means when we say point, line, and plane, we are describing relationships, and they have an intuitive notion of what that represents. Okay, so points. Point A, B, and C. Now you can definitely think the tip of a safety pin is like a point. Okay, a dot on a page is like a point. The I above notions is like a point. The edge of the letter C where it stops, that is like a point. Okay, so there's some ideas there. Next up, we've got a line. A line is, if you think about it, there are kind of 2 points typically that are needed to create a line. And what's great is that if I give you 2 points, you could use that straight edge and construct. Oh, that was perfect. Pretend that didn't happen. Okay, pretend that didn't happen either. Okay, we're going to go over to the line tool because I cannot draw straight. There. Oh, see, that looks like it's meant to be. So between these 2 points, I can create a line. But when you look at this line, every little piece on that line is a point. Like all these little things are points. So it's like there's a point here, there's a point here, point here, point here, point here. All of them are points. And between any 2 points, there's another point. And between those points, there's another point. So a line, like we saw back in chapter, what was it? 6, chapter 6 with fractions. A line is dense with points. That means between any 2 points, you can find another point on the line. Okay. So how do we write it though? So the symbolism is here. We can call the line by a name, like the line M. We can also say line AB and describe 2 points on the line. But most of the time we shorten it and we will give the 2 points and then put a symbol over the top with an arrow going in each direction. Now that indicates the line, which means it's extending infinitely in both directions. If it does not have the arrows on top, then what we would say is it's only this segment or piece of the line. Okay, so there's a difference. The notation is really important as we go forward. And because we could write AB, because we kind of read that left to right, just understand that is actually the same line as BA as long as you put the arrows over it. Okay. Okay. So again, we've got a kind of a one-dimensional shape, like a point. Then we have two-dimensional, which is like a line. Okay. And then we have three-dimensional. Okay. Now, three-dimensional shapes are going to be, but we add a third component, if you will. So a plane is a surface in space. It's technically, I guess, two-dimensional, but one dimension is a point. A two-dimensional is that line, and then but it's only in one direction. The plane is like that surface. So if you look here, this is kind of a good way to think about it. The tabletop itself has a line on this edge. It has a line on this edge over here. But what we're talking about when we say the plane is the surface. Okay, so like this two-dimensional surface here, that would be the plane. And we can label that plane with a single letter and say that one, as long as it's very clear what it is. If we have points on the plane, then we can label it with at least 3, because 2 won't do it, right? 2 would just describe a line. 3 is needed to describe the plane. And there's an interesting piece, because if I draw a line like this, AB, right, and I just pick any point to be my third point, I may end up accidentally putting my third point on the line, which does not describe a specific plane. And take a look at why. Take the edge of your desk, wherever you're sitting right now, right? Take one edge, That edge is a line, right? That line is included on the surface of your tabletop. Yes, but it is also included on this side of your table right here. Like the legs of your table come across and meet that edge and go down. That is also a plane. Just because there's nothing solid there doesn't mean it's not a plane. It's actually that plane. So this line is on a lot of different planes. And so we got to be really careful. So we don't want to choose something like this when we're labeling a plane. And we'll come to a word in a moment that helps us be more specific about that. Okay. So line, plane, point. Those are the three that we call undefined terms. Okay. And so take a look. A line is uniquely determined by 2 points. You need 2 points. Okay. So if I give you 2 points, there is one and only one line that contains them. Right. So we can talk about distance, the distance between P and Q. Okay. That's different. Now I want you to see the difference here. If I write PQ like this is the shape. It is a line. If I write PQ like this with nothing over the top and no description, this is a distance, also a number. Okay. Why is this important? Distances are numbers. Numbers can be added, subtracted, multiplied. Lines are shapes. You cannot multiply a shape. Shape is like this abstract concept. The number is kind of that solid, I know I can do something with this mathematically in terms of arithmetic. So be careful. When you're writing them, I am going to be looking to see that you're writing it correctly. So if you said, yeah, take a look at this line, we would tend to write like the distance from P to Q could be equal to the distance from A to B. This, as you can see, because there's nothing on top, is distances. Okay. When you put an equal sign between them because they're numbers. But the shapes themselves, maybe I have a line segment, I would say that shape is congruent to another shape. So when we have shapes, and I know this is going to be a little rough at first, but we're going to get there. When we have shapes, we say congruent. When we have numbers, we say equal. All right? Make a note of that because I know you're taking a lot of notes here. And I'm just going to go through these pieces. I'm not sure how much you have or remember. Collinear points. Collinear points means together, linear on a line. So linear and go together and make things that are on the same line. So when it says A, B, and C, you can see they're on the same line. You would say A, B, and C are collinear. All right. Now take a look at D. D is not on the same line as A and B. So you could say A, B, and D are not collinear. All right. Sometimes they'll say non-collinear, but most people just say not collinear. There we go. Done. Let's see here. There is a check. This is almost like a little theorem, if you will, right here down below, because notice it starts with an if, right? It's got an if and a then. So if you have 3 points and they are collinear, that means they're all on the same line. We say one of them is between the others. So when you look at it, which one is between is if and only if. If you go from A to B, that distance, and you add the distance from B to C, do you get the distance from A to C? Okay. So if I walk from A to B and I walk from B to C, is that the same as if I walked straight from A to C? And you would say, yeah. Okay. So if someone then said, let's check, this is good. They're giving you a definition, but they're not showing like, what would it be if it was not? Okay. So let's see here. Let's do one where it's not maybe. Okay. Okay. So here we go. So now let's check our own line. So here's a line, right? Here's A, here's B, here's C, and here's D. Okay. There they are. And I will say, aha, A is between B and D. Okay. Now, is A between B and D? Now, visually, you can look and say, no, that's not the case. But according to this definition, we'd have to check the actual numbers. So what I would check is I would check, okay, if A is between B and D, then I would walk from B to A and then from A to D. So let's see here, from B to A and then from A to D. And I compare that with my direct path from B to D. And I would ask, is AB that distance plus AD, right? And I should have written that BA. Sorry about that. Pretend that isn't here. BA plus AD, is that equal to BD? Right? And you'd look up here and you're like, well, BD, let's just say, is 2 units. And this is 1 unit that way and 3 units that way. 3 plus 1 is 4. No, false. So we would say A is not between them. Okay, so everything has a definition, and it's not just based on visual. We're going to see that in geometry. A lot of things we can spot visually, but we need to confirm them. And so this is what it means to be collinear. This is what it means to be between. Okay. All right. Next up, line segment. This is just like a line, except it ends. So it's finite. That means it has a specific distance or length, but this is what it is. It is a subset of a line. Go back to chapter 2, subset. It contains 2 points of the line and all the points between them. Remember the definition of between. So pick a point in between A and, like, pick a point on this segment. It will be between A and B. That's what we're talking about. You can also have half open. So this is possible. Now notice there's a little circle on top. So you can see that here if it's half open. So when you draw that little circle, let me choose a darker color. Sorry about that. When you choose that open circle and then you go over, when you put your point underneath it, like P and then Q, you are saying Q is included. But if I go back here, it's not including P. Okay. So there it is. But all the points between P and Q are still included. Okay. And you can have an open circle on one end. It means it does not include P, and a closed on the other. That's what it looks like right up here. Or you can have open circles on both. You could have closed then open, or open then open. Just what you want to include. Okay. Next up, let's see here. We have a half line, which is basically like this piece up here, but all we do is we add the arrow, which indicates it does not include point P, but it includes everything going in one direction on a line. So if you have the line AB right here, which we have drawn right down here, then what we're saying is, okay, if I just want to take half of that line, I could do it. Okay. Now you may ask yourself, well, wait a minute, what if I want to include that endpoint? If you want to include the endpoint, then we have a different name for it. It's called a ray. That means it does include the endpoint, but it goes through another point all the way out. So now be careful with this one. I'm going to tell you why. Because the notation, like up here, AB, that is congruent to BA. Those are the same shapes. Okay. Now, what do we know? If I say AB with an open circle here, right? Is that the same as BA with the open circle here? No, those are not the same because the open point is B or A. So we got to be careful. That is not the same. You would have to write BA with the open circle here, and then these two would be congruent shapes. Now, when you deal with a ray, we got to be very careful because if I say AB with a line going this direction, that means it starts at A, it goes through B, and continues infinitely. Okay. That's the idea. So you cannot turn that around and say that's the same as BA. So if someone said, are those congruent? You would say no. Those are not congruent. Okay. So the idea of a ray, we have the idea of a half line, all terms. And I'm sure you've got a sheet of terms right now that you can refer back to if you need it. Phew. What can we do? Once we have things like rays and segments and half open and not, we can intersect them and take the union of them. This goes back to chapter 2. So just remember, just a little refresher here, U is union. Okay. And since we're dealing with points, that means the point is on at least one of them. And if you see this shape, that is intersection. Again, this is back in chapter 2, 2.2, and 2.3, I believe. Intersection, and that means point is on all. Mostly there's two, so we could say both. Okay. So if someone gave me this and said, okay, take a ray, so I need points A and B. So in your mind, you could even sketch it. Here's A, here's B, and I'll draw the first one in blue. So A to B would start here and go this way. And B to A, okay, I'll choose a different color, would start at B and go this way, okay? Where do those intersect, right? What are all the points where they intersect? And if you need to, you could actually come and say, okay, well, wait a minute here. Let me see here. Well, they intersect everywhere here through everywhere here. Aha. So how would I write that final result? Because I need every single point that starts at A and goes over to B and ends at B and includes it. So this would say something like, oh, that's A, B as a segment with the points included. That would be the intersection. Okay. When you're drawing it, if it does not include a point, put a circle there just to kind of help remind you that it does not include that point. Right. Now, we have done this since chapter 2, but we're going to talk a little bit more about it. So we're going to say there are some things in math that we don't prove. We take them as true, and that is known as an axiom. You don't have to prove it. Based on the definition, it is guaranteed to be true. Okay. So here are some axioms that we will take as guaranteed to be true. There is exactly one line containing any two distinct points. So if I give you point A, you put point B down here, there is exactly one line that contains them. You can even picture the line. You could draw the line. If 2 points lie in a plane, okay, so these 2 points are on my screen right now on a plane, then the line that contains those points also lies in that plane. So that line is in the plane. We don't have a line that is outside of the plane, but then hits these two. Okay. If you wanted to think of that, think of like a sheet of paper, right? And if you had 2 points on the sheet of paper, is it possible to create a line that goes through them, but is not on the sheet of paper? And the answer is it might be possible if the line was curved, right? Right. So that's how we're kind of like, that's not a line then, right? That is violating this piece. So between two, we get exactly one line, and the line has to be in the plane. This one, in this case, you can kind of see comes up and out of the plane and then goes back down. So that is not possible in the axioms that we're dealing with. There's exactly one plane that contains any 3 distinct non-collinear points. So just remember, non-collinear, not in the same line. Any 2 points. Now, once we have those facts, we use those to create theorems, which we have to prove, like we've done throughout this course. But this one is going to be geometry is one where we prove a lot of things. Okay. Here's a picture from a book. This is grade 4, and you will see them doing a lot of naming rays, line segments, right angles, straight angles, acute angles. I mean, they're going through a ton of stuff, right? They're trying to get them focused on understanding these terms so we can use them as we keep growing. Okay. Oh, lines through points. So given 15 points, no 3 of which are collinear, how many lines can we create? So if you do have 3 points, you could see that you could make AB, you can make BC, and you can make CA. If you had 4 points, right? So if you kind of start, if you were the one doing this, you could be like, okay, I can do this. Good, you could. There's DE, DF, and DG. Then move up to point E and say, okay, from E, I have EG and EF. And then I'll move over here to point F and go F through G. Now, what I want you to notice here is a pattern, right? So if you start with point A and you make all the possible lines over here, you could make 2 lines from A. Once you're done with those 2 lines, you go to B, and there's 1 line you can make from B. The next one over here, I started with D. There were 3 lines from D. Then there were 2 lines from E, and there was 1 line from F. Interesting. If I do the same thing with 5 points, I will get 1, 2, 3, 4 for the first one. Then, right, 1, 2, 3 for the next, right? Then what do I get here? Then 2. And lastly, I'm running out of colors. So we'll do blue, I guess. And lastly, there would be 1 right there. So 1. Do you see what I'm saying? Look at this pattern. This is the same pattern that we saw back on day 2 of Math 105 with the canoe problem. It's very, very similar. So we get this beautiful pattern, which is actually just the sum of a sequence, and we can use that to create a beautiful formula that lets us calculate any of these pieces. And it's the same formula we saw for summing up a arithmetic sequence, 1 plus 2 plus 3 plus 4 plus 5. This is exactly what we have here. So this goes back to that beautiful sequence. So if you had 15 lines, you do not want to draw them all out. Look for a pattern, build the pattern, and then you can use it because you have 15 times 15 minus 1, which is 14. 15 times 14 divided by 2. Okay. And again, there's that sum of the sequence that we did back in chapter 2. They developed that same thing in chapter 8. So it's refreshed here with chapter 8. And there we go. Now, chapter 9 had something called combinations. We didn't cover chapter 9. That's covered. Cal State San Marcos covers that in their 3, I don't remember which course it was, but their 300 level course. They talk about those. Very, very cool. All right. So now we've got ideas of lines and making lines and creating lines and points and how they all come together. And now we get into planes. So now we deal with the same type of terms, coplanar. If you have coplanar points, it's points in the same plane. Non-coplanar points, no matter what you do, you cannot put them into one plane. So in order for that to happen, you have to have at least 4 points. You have to. Remember, because if you had 3 points, you guarantee to make at least 1 plane. If you have 3 non-collinear points, you guarantee to have 1 plane. So you need 3 collinear points, which is just 3 non-collinear points, and then 1 additional point, and guarantee those would be not on the same plane. Coplanar lines, those are lines in the same plane. And then this is this is interesting because we will deal with the concept of parallel. And you may have grown up with the idea, perhaps a teacher said, if 2 lines don't intersect, we call them parallel. Not the best definition, and here's why. So I want you to take a look, just look around wherever you are right now in a room. Okay. So in your room, let's just say there's, many walls, there's a ceiling, there's walls. So I want you to picture, you can see planes like the ceiling coming and hitting a wall. That creates a line, right? So that line is in both of those planes. We would call it coplanar. Okay. So I guess I'll try my best to draw a three-dimensional shape. So here, this is you in a room that looks a lot like a box. Okay. So how can I do this? Okay, I'm gonna try. So see this front face, maybe that's a wall. And then this top one, which is like the ceiling, where those hit, they hit a line right there. That line would be a coplanar line. It's shared between those two planes. Okay. Now I want you to think about that line. Okay, I want you to think about that line. And I want you to think about this line I'm about to draw. This line back here that's formed with another wall, basically two walls coming together, but not one of the front walls. Those two lines never intersect. Never. But they're not parallel because they're not kind of in the same direction. So we have a name for those. Those are called skew. Okay. Those are lines that cannot be contained in the same plane. Basically, they are lines that never intersect, but they're not in the same plane. So there's a little bit more to the definition of parallel. Parallel is lines that never intersect, but they are in the same plane. Okay. So intersecting lines, if you have lines, intersecting lines have exactly 1 point in common. Now, if you remember from what we were doing in chapter 8, we sometimes saw that you'd have an equation with two lines that look like this. They never intersect. We'd have lines that look like this where they intersect at 1 point. And then we had that weird case where it was basically a line that was like right on top of another line, right? If it's right on top, we call them concurrent. Oh, wait, sorry. If they're right on top, what we do in this case, that's not correct. This is, we would say they are the same line. Okay, so same line. If they intersect once, we call them intersecting. If they are concurrent, they are lines that intersect in a single point. So lines like this, yeah, I don't like that definition. The intersecting lines have at least 1 point in common to me, is what it should say, because then you have concurrent lines that intersect in a single point. Otherwise, this definition is the same. So we're going to change that. Intersecting lines is at least one. Okay, because this is intersecting lines and this is also intersecting lines. This one would be called concurrent, and this one would be called, I believe, identical. Okay. Phew. Lots of terminology here. Parallel, what does it mean? They don't intersect and they are in the same plane. Now we do have a new symbol. Some of you might remember this. If I say line M is parallel to line N, we draw two vertical lines really close to each other, right between them. Okay. All right. Now, the definition is, as well, that they have defining this to be a line is actually parallel to itself. Okay. So two distinct lines are parallel if they have no point in common, but they're allowing the definition to say a line is actually parallel to itself. They're using the word parallel here to mean same direction. Okay, so a line definitely moves in the same direction as itself. Two segments or rays are parallel if they lie on parallel lines. So a segment could be parallel to another segment, but what we do is we don't look at the segment itself, like AB, as just this little chunk. We consider the entire line, and we look at that. All right. Next up, now we deal with three-dimensional. So that was two-dimensional again on three-dimensional shapes, but now let's take a look at three-dimensional. I just asked you to think of two distinct intersecting planes. That's like the ceiling and a wall in your room. They will intersect at a single line. Those are called intersecting planes. Okay. Two planes are parallel if they do not intersect. Okay. So again, that kind of gives you a direction of a plane. Right. Now, when it comes to a line and a plane, there are two options. A line is either completely in the plane, and that means it intersects it infinitely many times, or it intersects it at exactly one point, like line F does, or it could be not in the plane whatsoever, kind of floating above it. Next up, we've got a line and a plane are parallel if their intersection is the empty set. What does that mean? The line, so you can't look at it and say there's infinitely many points that don't hit. You have to say there is not a single point where they do hit. That's what we would have to say. Okay. And then we could have something like a half plane where you think of a line, kind of like what is drawn here, cutting and kind of taking everything on this side, because think of the plane going infinitely. Okay, that would be like a half plane. Now, the way we label a half plane is we take the line, which we have line BC, and so we say BC with the line symbol, and then we append or we add on a point, whichever point on which side we want. So if this line cuts right down the middle, makes the plane into half of a plane, which half do you want? And so you could say, I want the side with A. Got it. So that's this side over here. Okay. There we go. All right. Good questions at the end. Skew lines have a point in common, can they? These are like always, sometimes, never, aren't they? Skew lines are parallel. Parallel lines have to be in the same plane. Skew lines cannot be in the same plane, so fail. Let's see here. And then we get to the idea of angles. So again, this section I told you is dense with words, but that's because this is the baseline. This is our basic notion. That's what this entire section is about. So now what you need to do is, what do we do? How do we form an angle? Well, an angle is formed with like a single point and then two rays that come together. And so those rays share only an endpoint. That's what they do here. That endpoint is called the vertex. The other pieces, which are the rays, are known as sides. The way we label this, we can just call this angle B if it's very, very clear. Okay. It may also have a number. So you may sometimes number an angle. That's not measuring the value. It's just calling it something. So we could call this angle 1. And you could also label it, and this is important, in a very specific way. You name the angle by putting the vertex in the middle and then the points on the rays on the outside. So A, B, C would tell me that the vertex is B. If you accidentally write CAB, then I'm not thinking of the angle that's depicted right here. I'm thinking of a very different angle because you said C, then A, then B. So now I am thinking of this angle when you write it this way. So you will have to get precise with how you write it so that we are all talking about the same thing. Okay. Once you create an angle, if you think about those half lines that are kind of created there, those rays, and kind of say, don't include them, the interior of the angle would be any point that is contained inside those rays. Okay. And lastly, adjacent angles. Adjacent angles, here's the idea. They share a common vertex. Okay. And they have to share a common side. Okay. And there's an extra piece here. This is the common side. The interior of your angles cannot overlap. So the interior of angle alpha is everything up here. The interior of angle beta is everything down here. Those do not overlap. So now take a look. What does it mean? What would it look like if they did overlap? What if I named angle QPS? Okay, so that's this one here, and angle QPR, right? So let me erase the other pieces here. So QPS, okay, that's good. And this happens with students all the time because they take that definition and maybe I'll do a QPR. So that's this angle right here. Okay. And they will check the points. They'll say, does it have a common vertex? Yes, common vertex, P. Do they have a common side? Yes, they actually share side, QP. That's the same. Okay. But there's one additional piece. The interiors cannot overlap. So the QPR interior is up here in yellow. But QPS interior is all of this. And you can see yellow and blue make green. We've got some green in there and we cannot have that. So you have to be careful with how you define them. All right. Lastly, how do we measure angles? Angles are measured typically with a protractor, which is just a device for measuring angles. We'll start to see that protractors are good for physical, but we can also use computers to measure the measurement of an angle, probably a little bit more precisely at times too. Okay, and here comes the fun part. Angles can be broken down into 60 equal parts called minutes, and each minute is broken down further into seconds. So we have certain measures are degrees, minutes, and seconds. And I want you to treat these like they are in a different number base. Okay, so when you have 29 degrees, 47 minutes, 13 seconds, and somebody says, hey, add another angle on there, add 15 degrees, 23 minutes, and 51 seconds. Then when you add, remember, just like we did in number bases, that this is like a base 60. So when you add and you get 64, right? Don't leave it as 64. Say, wait a minute, I have to regroup. So this would only leave me 4, and I would bring one more minute because 60 seconds is 1 minute with time and also with angles. So then I can add these together and it gives me 60, 71. And I'm feeling pretty good about 71 minutes, but I have to regroup. So say, no, that's 11 minutes and bring one more degree over here. And then 29 plus 1 is 30, plus 15 is 45 degrees. So there is how you would do that. Again, think of it like number bases. I think you'll be in good shape. If you need those number bases, go back to chapter 3 if you're saying, hey, I need a little bit more work with those. Okay. Now, can you convert forwards and backwards? Absolutely. Okay, so absolutely. And that is just taking decimal numbers. So when you have something like this that says 8.42, the 0.42 is decimal. We can say, wait a minute, 0.42, take 42% of 60, because there's 60 minutes in 1 degree. Okay, well, multiply. And then when you multiply that out, you'll get some number. Let me grab my calculator here and see what I get. 0.42 times 60 gives me 25.2. Okay, so what I have now is I have 8 degrees and 25.2 minutes. That's what I got. But see this 0.2? This is a decimal part of a minute. So I would take 0.2 and multiply it by 60 seconds. Okay, so 0.2 times 60 gives me 12. Okay, so this one was 25.2. So what I get now is 12. What does that mean? Bring it on down. You have 8 whole degrees. You have 25 whole minutes, and now you have 12 seconds. If you are going the other direction and converting from degrees, minutes, seconds back into decimal degrees, there's nothing wrong with that. Simply take this component, which is seconds, and divide it by 60. Add 25, divide by 60, and you'll get it back to the main piece. So just like what I did here, where I multiplied by 60, then subtracted, multiplied by 60, you're going to go backwards, divide by 60, then add, divide by 60, then add. So take 12 and divide by 60, you get 0.2. Add that to 25, press enter, divide by 60, and you get 0.42, and that is how you can go forwards and backwards. All right. Next up, so here is a kind of a protractor, but more of like an entire chunk protractor. This one is broken up into 90-degree chunks. So you can see you go from 0 to 90 and then go from 90 back down to 0. So you're only measuring in 90s. However, you can measure bigger than that. So going straight across would be actually from 90 to 90. So if you think about this, going all the way across, you would start maybe here and go, whoo. Well, the first chunk up to here is 90 degrees, and all the way across would be 90 degrees, and that would be 180 degrees to kind of make that half rotation. Okay. All right, let's see here. We have a new term as well, a reflex angle. Got to notice when you have an angle like this, there's another angle that kind of goes around. And so what we do is we say, typically whenever you measure an angle like this, you'll have one angle that's less than 180 degrees and one that is greater. We almost always refer to the angle that is smaller because the other one outside would be called the reflex angle. Okay. So we can always find that one. It's almost, we just kind of stick with the smaller one as a matter of convenience. All right. Let's see here. Oh, it says find the measure of BAC. BAC, if you know, oh, very common piece here. So this is a big one in geometry. We're going to see it the whole term. So if I give you a big chunk and then I give you a smaller piece, can you find what's missing? And so it's like big minus small, and that's going to be your missing piece. So yeah, you're going to be starting to do things like take the big one, the big angle, and subtract the smaller. But don't worry, it's base 60, so you got degrees, minutes, seconds, not a problem. Okay, I already did one of those, so I'm not going to do another one. All right. If you want to create angles, you can. Anytime you fold a piece of paper in half, you get a straight angle, which is 180 degrees. If you fold that one in half, you will get something that has 90-degree angles, and those are known as right angles. Some of you might remember that from other classes. A right angle, if you notice a right angle, you will see a symbol written like this. That symbol indicates it is a right angle, and that would be 90 degrees. Now, if you don't have a 90-degree angle, which would be a right angle, you're going to have something that is bigger than 90 or less than 90. And anything that is less than 90 is known as acute. Okay? Less than 90. Anything bigger than 90 is going to be known as obtuse. Right? Couple other pieces here. Anytime you have two angles that add up to make a straight line, we call them supplementary. Okay. So two angles. So anytime you have a straight line, if you cut another line across it like this, you will create two angles. We'll call angle A, angle B. And if you add those together, if you get 180, we would say A and B are supplementary. If you did draw a line and you came straight down and you were like, woohoo, right? And you made a right angle, you could do the same type of thing where you kind of create another angle over here. And my two angles add up to 90 degrees. That is known as complementary. So when they add up to 180, supplementary. So I think of supplementary with starting with an S is a straight line. Complementary makes the right angle. And I know it's spelled differently because it's a completely different word, but if you play on words a little bit, if you give someone a compliment, I know it's spelled different, right? But this is just a way to think about it. Compliment, isn't that the right thing to do? Complementary angles add up to a right angle. Okay, complement. There's usually a math joke where two angles are like talking to each other and they say, oh, you are so pretty today. Oh, you are so nice, right? And they're being very complimentary because they add up to a right angle. That's It's math humor. Eventually, you're going to actually enjoy it. Okay, so here's an acute, here's right, here's obtuse, and then you have straight angle. So these are the four types of angles you're going to have that go from 0 to 180. Now, do remember, you can have an angle bigger than 180, right? So if this goes here, think about an angle that comes all the way over like this, right? And you say, ooh, that angle is like 210 degrees, for example. And you're like, that's fantastic. But once you make that angle, you are also making this angle. If that's 210 degrees, that means this one over here is 150 degrees. This one that I'm drawing in green down here is simply an obtuse angle. And the 210 would be the reflex angle. So again, most of the time we want to focus on things that are in this chart. All the other ones are just 360 minus whatever I was just saying. Okay. And what else do we have? Yeah, when we were doing clock arithmetic, we would start with a ray, make a rotation. The rotation was 360 degrees. And you should know there is a direction as well. So on a clock, when we were doing clocks, and it was like 3 o'clock, then we would talk about this hand. The hands are moving in this direction. That direction is known as clockwise. Okay. If you go the other direction, so if I go this direction, it's clockwise. Okay. If I go the other direction, right? So now things are going backwards, if you will, then we call this counterclockwise. So that tells you kind of how something is rotating. And the reason why that's important is if I'm talking to someone and I say I've got a ray and I'm sweeping out an angle, when I know my starting point goes from A to B, when you tell me where my next one's going to be located, I need to know which direction to turn. So if you say turn 30 degrees, I still have to ask, do you want me going in a clockwise direction or a counterclockwise direction? You see, those make different angles, right? So we need to know a little bit more sometimes, and that's why that is important. And I think this is the last big piece, circles and arcs. So we had lines, we had planes, we had all these three-dimensional pieces for straightness, in a sense, a straight line. Now we're going to get into curves, and the curve that we make mainly is a circle. A circle is the set of all points that are the same distance from a center point. The center point is fixed. The radius is that fixed distance. You'll see the radius noted here. If you make a segment from one point to another point and it goes through the center, you do not have a radius, you have what is called a diameter, right? You also have curves on this shape. A curve that is a part of the circle but not the whole circle is known as an arc. And you also have line segments through different parts of the circle that may or may not go through the center. If it goes through the center, we call it a diameter. If it doesn't go through the center, we call it a chord, C-H-O-R-D. So again, I know this is a lot of terms. Make a little cheat sheet for yourself if you need it, because this is just the definitions. Definitions are good to know because that's how we're going to word questions. Okay. All right. Different types of arcs. Yes. If your arc is, let's see here. When you're naming your arc, how do I want to say this best? When you're naming your arc, you have to be very clear on how it is made. We typically put 2 points on the circle